In class, let's take a look at your notes for section 6.3. I apologize up here at the top that the notes actually say 6.2. That's just a typo mistake, but this is actually the correct section for 6.3. But what we're going to be revisiting is some stuff that we talked way back in chapter 1, and that is, first of all, dealing with how we go about transforming, okay, random variables. And that's going to be the biggest piece today. Later on in 6.4 we'll talk about how we go about combining them. But today's just going to be really the focus on the transformations. So the first part of today's notes is just a revisiting what happens to certain measurements of center and spread and also shape, okay, when we talk about linear transformation, meaning we're adding some number to every single data point, or we're multiplying some number by, or we multiply every data point by some number. So what happens? Okay? So to recall, when we add, okay, so adding the same number, whether it's a positive number 0 or a negative number to each observation, okay, what it does, if you remember, it changes the center and the location. Okay, so we're going to be adding A to measurements of like mean, median, quartiles, and percentiles. Okay, however, this is the very important part, does not change the shape, and it does not change measurements of spread. The key one that we'll focus on is standard deviation. For center, we'll focus on mean. Now, when multiplying, so that's where we multiply, even if it's a positive number or a negative number. I suppose there is 0 also, but that would just cause everything to be 0. Okay, it multiplies or divides the measurement of center. So it's going to change all these measurements of center up here. It multiplies the measure of spread by the absolute value of B, because since spread is a positive, needs to be a positive measurement, if you're multiplying by a negative number, need to realize that a distance can't be negative, hence why it has those bars there for the absolute value. However, again, shape doesn't change, okay? So if it's a uniform distribution, it's going to stay a uniform distribution. If it's normally distributed, your shape stays. So these linear transformations have no impact on shape whatsoever. Or I should say it like this, the center is impacted by both adding and multiplying, but the measurement of spread is only affected by multiplying. So, to kind of summarize what we're talking about here, okay, as it says here, if you're doing some sort of linear transformation, so A is the adding part, it's your y-intercept. B is the multiplying part, it's your slope, okay? Then what happens is your new mean of y, which is that new random variable y, can be found. So the mean of y can be found by taking a plus b times the mean of x. Likewise, the standard deviation of y can be found by taking the absolute value of b times the standard deviation of x. Notice how this doesn't have the plus a. It doesn't change it. So the biggest key is, can you write your linear transformation and then apply the rules? So let's take a look at the example here at the bottom. So number 1 here, it says a large introductory stats class, the distribution x equals the raw scores on a test was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. So right away, I'm off to the side here, I'm going to say mean of x was 17.2, standard deviation of x was 3.8. They're giving you those values, and notice how it says what x is. The professor decides to scale the scores by multiplying the raw scores by 4, so we're multiplying by 4, and adding 10. So I'm telling you right there what the linear transformation is. So in part A says it defines the variable y to be the scale score of a randomly selected student for this class. So I need to define y. So y is simply going to be, I'm multiplying the raw scores by 4, so I can think of it 4x, and I'm adding 10. So right there is my linear transformation. So it says find the mean and standard deviation of y. So if I'm trying to find the mean of y, I find it by going a plus b times the mean of x. Okay? Notice how here is my b value. It's the number in front of the x. Here's my a value. I know I wrote it in reverse order, but you should still be able to identify the y-intercept and the slope. So in our case, our mean of y is going to equal 10 plus 4 times 17.2. So now if you plug that into your calculator, you should have a new transform score of 78.8 points. Now we do the same thing for the standard deviation, but we have a different formula. Absolute value of b, times the standard deviation of x. So our standard deviation of y in our case is going to be the absolute value of 4 times 3.8. Well, the absolute value of 4 is just 4. So 4 times 3.8, I believe, is 15.2 points. Okay. All right, so that takes care of A. So now in part B, it says, what's the probability that a randomly selected student has a scale test score of at least 90? So the question becomes, what does my distribution look like? Well, up here, notice how it says approximately normally distributed. Now that applies to x. Okay? X was normally distributed. But as we saw up top, the shape doesn't change. Okay? So since the shape does not change, the distribution of y is normal, or at least approximately normal. So I can treat this problem like a normal distribution. So I'm looking for, well, what's the probability of having a transform score y of at least 90? Greater than or equal to 90. So now, if I think about this, here I have my mean and standard deviation right here. So if I'm thinking about this visually, I'm thinking, all right, it's normally distributed with a mean of 78.8 and a standard deviation of 15.2. So I'm trying to see what's the probability of having a score of 90 or greater. So I'm looking for that area. So right away, I'm hoping you're thinking z-scores. So I'm going to convert this to a z-score. Z is equal to my score 90 minus 78.8 divided by 15.2. If you calculate that out and round it to 2 decimal places, you get 0.74. So now what it's saying is we're trying to find what's the probability that I have a z-score greater than or equal to 0.74 standard deviations away from the mean. So if you remember on our calculator, we can calculate this out by doing our normal CDF. This is where the picture helps because we're going from our z-score to positive infinity. So I would be typing in 0.74 to positive infinity, so I type in a bunch of 9s, and that gives me my area, 0.2296. So we can now answer the question, the probability that a randomly selected student has a scaled test score of at least 90 is 0.2296. All right, that takes care of the first page. So, as we go to the second page, number 2 here, it's just more practice and just re-emphasizing all of these linear transformations and also reviewing some of the concepts, okay, that we are covering. So, excuse me. So we're going to be doing some stuff that we've been doing in 6.1 and 6.2 here. So El Dorado Community College considers a student to be full-time if he or she is taking between 12 and 18 units, okay, or credits, you could say. The number of units X that a randomly selected El Dorado Community College full-time student is taking in the fall semester has the following distribution. So you can see from 12 to 18 with their respective probabilities. So the first question says, find the mean and standard deviation of this distribution. Okay? So, to find the mean, remember we're finding the expected value. So we're taking each number of units and timesing it by its respective probability. So we do that for all of the credits. So as you can see, I'm going 15 and 16 and 17 and 18. So if I plug that into my calculator, you can check, you should get 14.65. So take a second and pause the video, plug it in your calculator just to make sure you're getting the correct value. All right, the next thing we want to find is the standard deviation. Remember from yesterday, in order to find the standard deviation, you actually have to find the variance first. So we're going to find the variance, then take the square root of that to get our standard deviation. So this takes a little bit more work. So you're taking each of your scores, minusing the mean, squaring that, and timesing it by its probability. And then we do it again for each and every single data point. So this is the one that takes probably the biggest calculation that you do in this class. I'm talking for the whole term. Let's see, 15 minus 14.65 squared times 0.3 plus, and then we're at 16 minus 14.65 squared times 0.1 plus 17 minus 14.65 squared times 0.05 plus 18 minus 14.65 squared times 0.15. So again, pause the video, plug this into your calculator. If you use parentheses like I have, you can actually type the whole thing at once. You actually only have to have this first part in parentheses squared. You can then go times 0.25 plus this part in parentheses squared times 0.1. So really you don't need the parentheses around the probabilities. I do it so you can easily see the separation when writing it by hand. When you do, hopefully you unpause now and see that you get the same answer as I do, 4.2275. Again, that's the variance. So the standard deviation is the square root of this particular value. So we get 2.056. So if we're thinking about what these represent, if I pick a random student at this El Dorado Community College, the average number of credits they take is 14.65. The number of courses will differ on average from this mean by 2.056 units. okay, for a randomly selected student. Okay? All right, so these two values are going to become important in our next couple calculations. So in part B, it says at El Dorado Community College, the tuition cost for full-time students is $50 per credit. Define T as tuition charge for a randomly selected full-time student. Okay? So basically what T is going to equal is $50 times the number of credits or the number of units. So now it says find the mean and standard deviation of T. Okay? Well, remember how our linear transformations work. So the mean of T in this case should equal, okay, A plus B times the mean of X. So in our case, the mean of T, there is no A value, so it's just going to be 50 times the average number of credits. So if I go up here, 14.65. So now what we're finding is basically the average tuition cost for a randomly selected student at this community college. Then we're finding the standard deviation. Again, absolute value of B times the standard deviation of X. So in our case, the standard deviation of T, 50 times the absolute value of, whoops, I apologize. 50 should be in the absolute value. The absolute value of 50 times 2.056. So absolute value of 50 is just 50. So the average tuition cost will vary for a randomly selected student by $102.80. All right, so now C says, in addition to tuition charges, define each full-time student each full-time student is assessed a student fee of $100 per semester. It says define C as the overall cost for a randomly selected full-time student. Find the mean and standard deviation of C. So now when I look at C here, I can think about it like this. C equals, well, we start with that tuition cost, so 50x, but they also get assessed a $100 fee. Okay, per semester. So now, using these same formulas up here, if I want to find the mean of C, it's going to equal A plus B times the mean of X. So in our case, the mean of C is going to equal 100 plus 50 times 14.65. Basically, we're adding another $100 on top of it. So notice how it's gone from $732.50 to $832.50. The standard deviation of C, however, think about this. You're only doing the multiplication. So the standard deviation of C, however, that 100 does not come into play. So you're just going the absolute value of 50 times the number of credits, again, 2.056. which ended up being $102.80. So that didn't change. So, last but certainly not least, what we try to emphasize here with linear transformations one last time, okay, is what happens, okay, to the shape, center, and spread of all of these three distributions. Okay? Well, if I start with shape, the shape of all three distributions will be the same. They do not change. Okay? As we saw that on the previous problem when we were talking about the transformed test scores. If the original shape was normal, so will be any transformed distribution will also be normal. Now, when we take a look at the mean, this is the one that probably changes the most. I'm going to slide this up here. So, first of all, we see that the mean of T is 50 times larger than the mean of x, and C is 100 more than the mean of t. So we've talked about center. Spread, we're going to look at the standard deviations. We can now say both T and C are 50 times bigger let me rephrase that, I apologize. Both T and C are 50, well, I'm going to keep it like that. Sorry, are 50 times bigger than X when comparing their standard deviations. All right, so again, it's just emphasizing this fact of how linear transformations, okay, impacts, okay, and changes our values. All right, so that ends our notes here for 6.3.